You're on the Argman YouTube channel, the channel for minimal value math videos for frustrated mathematicians. So this is our real analysis class, lecture 8 on completeness. So if we recall from our last video, we looked at Cauchy sequences. And that was just for all epsilon greater than 0, there's a natural number n, such that if n and m are greater than or equal to m, there's no big M, there's a big N though, then a n minus a m, any pair is less than epsilon. Also, we looked at proofs for convergent sequences are Cauchy, and that Cauchy sequences are bounded. And now we're going to be looking at something called completeness. Let's define that. So we say X, a subset of R, is complete if every Cauchy sequence in X converges in X. So let's look at an example. Take X equals 0, 1. So, and an is equal to 1 over n plus 1 in X. An approaches 0, and that is a Cauchy sequence. But 0 isn't in X, so X isn't complete. Another example, let's look at the rationals. So if we look at the sequence 3, 3.1, 3.14, and so on, this sequence is in the rationals, but if this is constructed so that it converges to pi, so let's just write it like the same thing above goes to pi, and that's not in there, so the rational numbers aren't complete. And that motivates why we even care about the real numbers. It's because there's these irrational numbers, and what it turns out is that the real numbers are themselves complete. So theorem, let's call this the completeness theorem. Just has this simple statement: R is complete. And just so we remember what complete means, because it's all the way up there, every Cauchy sequence in R converges in R. So we just substitute x for the real numbers. So that's the subset we care about, which is just the whole set. So proof. This might be a long one. So strap in. Let an be Cauchy and the real numbers. Let epsilon greater than 0 be given. So we know from the definition of being Cauchy that there's a natural number n1 such that an minus am is less than, we'll fill this in later, it just has to be a positive number for nm greater than or equal to n1. So since an is Cauchy, an is bounded. So by the Bolzano-Weierstrass theorem from before, we know that every sequence has a convergent subsequence. An has a convergent subsequence that looks like a sub n to k, and let's say it has limit L. Because it's convergent, this L must exist in the real numbers. Since n1 is less than n2 is less than n3, and so on, we can fix k such that nk is greater than or equal to n1. Water sip. Moreover, there exists another constant, n2, natural, such that a sub n sub k minus L is less than, and we'll leave this blank again, just needs to be positive, for all k greater than or equal to n2. Now suppose that k is fixed such that n sub k is greater than or equal to n sub 1, but also we choose k to be greater than or equal to n sub 2. Then for any n greater than or equal to n1, we have that an minus L, this limit, is greater than or equal to, we're going to do a trick we've done before. This is just adding, subtracting a and k, and then applying triangle inequality. And that is less than something is equal to epsilon. So we want this to be plus this to be less than or equal to something that is equal to epsilon. So let's put in epsilon over 2 plus epsilon over 2, just so it's nice and everything's the same. And if it wasn't clear where these came from. So this is less than epsilon over 2 because of it being Cauchy. So an minus am is less than epsilon over 2. So if you sub in m equals n sub k, we know that n sub k is greater than or equal to n1, so it satisfies that condition. And for this one, it just comes from the one right here, which is true for any k greater than or equal to n sub 2. And we fixed it so k was greater than or equal to n2. And so we have an minus L, absolute value, is less than epsilon. So that thus it converges, and it converges to something in L, in the real numbers, if that wasn't clear, because this must converge in the reals. Okay, let's see how we can apply this theorem. So let's show that the closed interval from 0 to 1 is complete. A sub n is Cauchy in 0, 1, which means an converges to L in R. And since an in 0, 1 for all n in n, we also have that L in that same interval. This is a property of limits called limits preserving order. So since the limit is inside of the closed interval, this is complete. As another example, say a sub n is, this is going to be awesome. It's not really a mathematical term, but we're just going to invent this property. If for all epsilon greater than 0, there is an n natural number such that a n plus 1 minus a sub n is less than epsilon. Let me write that nicer. For all n greater than or equal to n. So we're going to show that let's see, what are we showing? We're going to show that first off, it's clear that any Cauchy sequence is awesome, because if you just sub in m equals n plus 1 in the Cauchy definition, you get the same, you get the statement above. So let's look at some sets which are awesome. Let a sub n equals 1 plus 1/2 plus 1/3 and so on. It's defined as n 1 over n. So it's a sum. Then a sub n plus 1 minus a sub n is equal to 1 over n plus 1, which approaches 0. So an is awesome. Now, suppose that an has limit L. L is equal to 1 plus 1/2 plus 1/3 plus, just keep writing terms, 1/6 plus 1/7 plus 1/8, and so on. It's going to be clear why we did this soon. Is greater than 1 plus 1/2 plus 1/4 plus 1/4 plus 1/8 plus 1/8 plus 1/8 plus 1/8 plus 1/16 plus 1/16 plus 1/16. If we do that 8 times, and you just keep going on, this is going to be equal to 1 plus 1/2 plus this is equal to 1/2, so 1/2. This is equal to 1/2, so another 1/2. Again, this is equal to 1/2, so another 1/2, and so on. And here, an diverges. So this one is awesome, but it diverges. So that's it. To recap what we've done, so we constructed R, the real numbers, and showed it has an order and that it's complete and that all of its Cauchy sequence converge in itself. To do this, we showed the least upper bound principle, that the supremum of a bounded set bounded by above set exists. And then we showed the monotone convergence theorem. Excuse me. And from there, we showed the nested intervals theorem, or lemma. I'm always unsure if there's an S on that one, but there are multiple intervals, so I'm just gonna write S. Nested intervals lemma, and then showed Bolzano-Weierstrass using that one. And then use Bolzano-Weierstrass to show that the reals are complete. So that's where we are in class. And this is how we got here. It actually is true that these have if and only if relationships, but this is the path we took. And that's it for this lecture.